In the last video, we took a look at how we could calculate derivatives of logarithmic functions, and I actually want you to go ahead and see if you can practice those ideas right now on example number 2. I'm going to ask you to actually go ahead and take a look at parts A and B of example number 2, and using the theorem that we have up above, try to calculate the derivatives. Now, go ahead, pause the video, and when you unpause the video, you'll see that I'll work through the solutions for parts A and B, and I'll talk us fully through part C. All right, so hopefully you did actually take some time to go through and do that. Let's take a look at what these derivatives would look like. So if I was going to compute my first derivative here on part A, notice that I start with the natural log of stuff. So I have a natural log of a whole bunch of stuff on the inside. Now, according to the rule that I have right here, my derivative would automatically be 1 over all of the stuff that's on the inside of that logarithm times, of course, the natural log of my base, which in this case is natural log of e. Now actually the natural log of e is 1, so if you didn't bother to write this down, that's also perfectly fine, and you could have just had 1 over sine. But now, since my inside is not just an x, I would have to follow up with a chain rule, and I have to say the derivative of the sine function is now going to be cosine of x. So I really have cosine of x over the sine of x, and actually if you wanted to, you could rewrite that as cotangent of x. Okay, so there we go. That's what I would do for part A. In part B, I notice that I don't have a natural log with a base of e, but I have a log with a base of 10. And so again, I would do the same thing for my derivative pattern. I would start by doing 1 over everything on the inside of my logarithm. So I would take all of this, and I have 1 over that. Then I would just have times natural log of the base. Now I can look at the inside of the logarithm, and I notice it's not just x, so I'll do a chain rule here. I'll take the derivative of 2x plus cosine x. The derivative of 2x is 2, and the derivative of cosine x is minus sine x. So I write that as a subtraction of sine x. So there we go. I have this. So hopefully parts A and B weren't too terribly difficult. It's a little weird maybe at first to think about how parts A and B work when I have this input on the inside that's not just a standard x, but happens to be a whole function. But hopefully you can see it's the same basic idea, that I just take 1 over that entire input and then just follow up with the chain rule. Well, let's take a look then here at part C. Here I'm going to have the natural log of the absolute value of x, and I want to try to take a look at the derivative of this. Now, what's kind of weird here is that I don't really have any derivative rules formed for taking derivatives of absolute values, nor will we actually define any absolute value derivative rules this semester. Instead, we think about what the absolute value function really means. So let's take a look here. I'll start off by saying that we note that y is actually able to be kind of re-expressed as a piecewise function. Notice that if the value of x was 0 or greater, then I actually, well, I really shouldn't bother with the value of 0. I can't use the value of 0 in here because I have a natural log. But if the value of x was, say, just greater than 0, then these absolute value bars really serve no purpose, right? They don't do anything to the value of x. And so I can just write this as natural log of x. However, if it's the case that x happens to be less than 0, if x is a negative number, then those absolute value bars actually do make a big difference. But I can get around that by just saying I'll take that value of x that's negative and I'll multiply it by a negative 1. So if I have this, I could easily go ahead now and try to compute the derivative, but now just kind of each piece. So the derivative of natural log of x would just be 1 over x. Of course, that's my derivative as long as I'm working on the top piece. The derivative down here would require the use of a chain rule, which would be 1 over negative x, and then times the derivative of negative x, which is negative 1. This is, of course, then if x is less than 0. Now, of course, if I simplify this down, what I'm really ending up with is that I have a derivative of 1 over x if it's the case that x is greater than 0, but actually I get a derivative of 1 over x if x is less than 0 as well. And so I can almost kind of summarize all of this together as just 1 over x. So the derivative of the natural log of the absolute value of x is also just 1 over x. The only difference here is that this original function, at least compared to the basic natural log function that we would have had up here, is that this function can actually take negative value inputs, right? I can plug in -2 here, whereas in the original natural log function I can't. So this example here is actually going to be super important. We're going to come back to this in chapter 5. And so you might want to make a note of that actually in here, because at some point we will return to this. So we will return to this fact in chapter 5. It's actually going to be really important. And so it's nice to kind of mark that right now. So that way, when I ask you later in chapter 5 to come back and look at this fact, you'll be like, oh yeah, he did tell us about that. Okay. So hopefully these examples give you a little bit of an idea of how we're doing derivatives of natural log functions. And of course, if you need more practice on that, you can take a look at the associated worksheet problems. In the videos to come, we're going to talk about how we can now use derivatives of logarithmic functions to our advantage to take derivatives either more simply for certain types of functions, or take derivatives of functions that maybe we didn't actually have the ability to take derivatives of prior till now.